Welcome back, everybody. This is Mr. Johnson with the bonus lecture on the ideal gas law, a little bit more about it, what its variables mean, the units that those variables need to be in, a little bit more about R, the ideal gas law constant, and then I'm going to derive the combined gas law for you, which was not done in the lectures you've watched so far. We're on page 475 of our ebook, and I'm looking at this highlighted section here that says the ideal gas law is equal to the pressure of a gas times the volume, which is equal to the number of moles N times the ideal gas law constant R times the temperature T. PV equals nRT. It's sometimes referred to as PV-NERT. PV equals nRT. This is not an equation you have to memorize. In fact, soon will I reveal to you the equations and constant sheet, which has on it a whole bunch of things that you, again, don't need to memorize. The pressure of the gas can be in a variety of units. It could be in kilopascals, it could be in atmospheres, it could be in millimeters of mercury, which is the same thing as torr, or it could be in psi. The unit for pressure in the ideal gas law can vary, but it has to agree with the unit for pressure that is in the version of R, the ideal gas law constant you use. And I'll talk about that in a moment. The volume always has to be in liters, because we will see that the unit for the volume in the ideal gas law constant is always in liters. Units have to agree to cancel. Moles is always moles, so N will always be moles. Again, we'll talk about the ideal gas law constant here in a moment. And then temperature in all gas law problems needs to be in Kelvin. So if a temperature is given to you in Celsius, you've got to convert it to Kelvin by adding 273. So again, the unit for pressure can vary, but it has to be the same as the unit for pressure in R. Volume is always in liters. Moles are moles. Ideal gas law constant, again, can vary. We'll talk about that in a moment. And temperature is always in Kelvin. So we're now on page 477 of our ebook, looking at this section here titled R values provided in the AP exam table of constants, which again I'll be showing you shortly. The ideal gas law constant is the proportionality constant that exists between the pressure, the volume, the temperature, and moles of gas. And it doesn't change. Under different temperatures, different pressures, different volumes, the ideal gas law constant stays the same. There's three common options we can use for R. The first one is 8.314. That's liters times kilopascals over moles times Kelvin. Notice the unit in the R that is 8.314 for pressure is kilopascals. So if you are using kilopascals for pressure in the ideal gas law, you want to use this R, the one that has kilopascals in it. Again, the unit for pressure you use in PV-NERT has to agree with the unit for pressure in R. The second one, 0.082606, has a unit for pressure of atmospheres. If you're using a unit for pressure of atmospheres in the ideal gas law, you have to use this R. The final R has a unit for pressure of torr, which remember is the same as millimeters of mercury. And again, if the unit for pressure you're using in the ideal gas law is in torr or millimeters of mercury, this is the one to use. This first gas law constant, by the way, is 101.3 times greater than the second one, because that's how many kilopascals there are in an atmosphere. That's why these values are the way they are. Flipped my page, I'm on 478 of the ebook, and I'm going to be solving practice problem 1 for you here, which is a fairly typical and straightforward ideal gas law problem. All right, so here we go. Find the volume of 1 gram of water if it were converted to the gas state at its boiling point of 100 degrees Celsius at standard atmospheric pressure. If you're given one set of conditions under which a gas exists, as opposed to what you'll see me talk about in a little bit, then that's going to be an ideal gas law problem. And all the variables that the ideal gas law has in it are the variables that are established in this problem. With the exception of mass, this 1 gram, which is mass, has to be converted to moles to be able to use it in the ideal gas law. So I've rewritten the ideal gas law here, PV equals nRT, reminding you that the unit for pressure will vary, depends on the unit that you have for pressure in R or vice versa. Volume again in liters, moles are moles, and the temperature always has to be in Kelvin. So we've got to convert 1 gram of water to moles, 1.00 grams. There's, in 1 mole of water, 18.02 grams. So when we divide 1 by 18.02, we 0.055 moles. Oops. Get back up there, little buddy. All right, I'm going to rewrite PV equals nRT. Standard atmospheric pressure, remember, we're given it in the problem, is either 1 atmosphere or 760 millimeters of mercury / torr or 101.3 kilopascals. I'll go with kilopascals because I know I can use whatever unit for pressure I want as long as I pick the correct R. So 101.3 kPa, could have gone with atmospheres or torr. The volume always has to be in liters. That is what we're finding. So I'm going to go X for liters. Moles was 0.055 moles. I'm going to pause because now we need to think, what R do I need to use? I need to use the R that has kilopascals in it. If you remember a moment ago from our book, the one with kilopascals is 8.314. So I'm going to put 8.314 kPa times liters over moles times Kelvin. And then I've got to put the temperature over there. I'm given the temperature of 100 degrees Celsius, but remember we've got to convert all temperatures in all gas laws to Kelvin. To convert Celsius to Kelvin, you add 273 to Celsius. 100 plus 273 is going to be 373.0 Kelvin. So we solve for X, divide both sides by 101.3 kilopascals, and we get a final answer of 1.68 liters. I'm now going to derive for you what's called the combined gas law. And everything I'm talking about is explained in more detail in the first 7 or 8 pages of 8.2, section 8.2 on our book. It's got the combined gas law written up there again, PV equals nRT. I'm going to manipulate that to get R by itself. And I'll end up with P times V over N times T equaling R. Again, R is this proportionality constant that exists between pressure, volume, moles, and temperature. What I'm now going to do is add little subscript 1s to each of these variables, P1, V1, N1, and T1. And what those represent is the initial pressure, initial volume, initial moles, and initial temperature equaling some constant R. Or this is the pressure, the volume, and the moles, and the temperature under one set of conditions. Imagining the conditions could change. The temperature could change. The pressure could change. The volume could change. Well, if the pressure times the volume over the moles times the temperature of a gas at any conditions equals R, then we could say that that same R is equal to the pressure under a new set of conditions times the volume under a new set of conditions over the temperature under a new set of conditions times the moles under a new set of conditions. I switched the order of N and T, but that doesn't matter. And if this is true, if the pressure times the volume over the moles times the temperature under a one set of conditions is equal to the same R as the pressure, volume, temperature, and moles under a different set of conditions, then they're equal to each other. I can get rid of that R in the middle. And magic, it's gone. So there is the pressure, volume, moles, and temperature under one set of conditions equaling the pressure, volume, temperature, and moles under a different set of conditions. But in problems where the conditions of a gas changes, the pressure changes, maybe the volume changes, possibly both change, the amount of gas won't change. The moles of gas in a problem like this stay constant, so we can cross out moles from this expression. And what we're left with is the combined gas law, which says that the initial pressure times the initial volume over the initial temperature equals the new pressure times the new volume over the new temperature. P1 times V1 over T1 equals P2 times V2 over T2, the combined gas law. This is something you do have to remember or be able to derive on your own. It is not on this equations and constant sheet. Let's see how we use this in a practice problem. Again, this is the combined gas law, allowing us to figure out maybe what the new temperature of a gas will be when the pressure and volume change, or what the new volume might be when the pressure and temperature change. Here we go. And we've jumped back to page 475 of our ebook, and I'm going to solve practice problem 2 with you here, 475 of our ebook. There's also a great sample problem if you want to look on the prior page, 474 of our ebook. I'm going to go to my whiteboard now. All right, we got a problem here about Zippy, who's got a wart on his big toe. The doctor's using a compound, a gaseous nitrogen compound. Notice that it's giving us the volume of the nitrogen compound to begin with, 18 liters. It's giving us the pressure. It's giving us the temperature. And then it's asking us what the new volume will be at a new temperature and pressure, at standard temperature and pressure. That's a combined gas law problem, of course, because there's a new set of conditions under which this gas exists, one of the variables we need to find. So we're going to write the combined gas law, P1 times V1 over T1 equals P2 times V2 over T2. And remember, if one of these variables isn't mentioned, if there's no mention of temperature in the problem, you can just eliminate it from the combined gas law and have just P1 times V1 equals P2 times V2. as well. If pressure weren't mentioned at all, meaning the pressure is held constant, then you could eliminate it and you just have V1 over T1 equals V2 over T2. So this law can be used for just 2 of the 3 variables as well. So I'll plug in the initial pressure, 44.4 kilopascals. I'll plug in the original volume of 18 liters. And I'll plug in the original temperature, which remember always needs to be in Kelvin. So we've got to add 273 to 125. 125 plus 273 is 398 Kelvin. 398 Kelvin. The temperatures in all gas law problems always have to be in Kelvin, in ideal gas law problems and in combined gas law problems. Temperatures in Kelvin. But the pressure units can vary in a combined gas law problem. They just need to be the same on both sides. So as long as they're kilopascals or atmospheres on both sides, we're fine. Same thing with volume. The units for volume can be anything in the combined gas law as long as they're the same on both sides. Typically, they'll be in liters, though. So for P2, that's standard pressure. Remember, standard pressure is either 1 atmosphere or 760 millimeters of mercury / torr or 101.3 kilopascal. So I'm going to go with 101.3. So the unit matches what I have on the left. The new volume is what we're trying to find. And the new temperature is standard temperature, which remember is 0 degrees Celsius. Add 273 to that, we get 273 Kelvin. So at this point it becomes algebra. What I'll end up doing is multiplying the left-hand side by 273 over 101.3 to get those away from the right-hand side. And I'll end up with a V2 of 5.41 liters. And just to remind you once again, all temperatures and all gas law problems need to be in Kelvin. For combined gas law problems like we just solved, the units for pressure don't matter as long as they're the same on both sides, and that's true of volume as well. Good luck, folks. Enjoy your gas law problem solving.